Yeah, good afternoon, everybody. So today I plan two things. So the first thing that I want to do is keep my promise and tell you how to really solve the knapsack problem. I mean, we had this algorithm that has cubic running time, which is quite okay for an NP-hard problem, but we want to be even faster. So as I mentioned, with this Nebenhauser-Ullmann algorithm with cubic running time, you can maybe solve instances with 10,000 items, but then you already run into trouble, usually. But now we want to solve instances with millions of items. And I will present you essentially one heuristic to do so. That part won't have too many proofs. Actually, it will have no proof at all. It's just the heuristic part. And then I will switch to a more theoretic topic, namely the question, which problems get easy if I perturb the input and which problems stay hard? There's actually a very nice characterization. But let us start with this heuristic. And this heuristic is called core algorithm. And it's based on something that we saw in Eden's first lecture, namely on the fractional knapsack problem. So what we want to solve is the usual binary knapsack problem, but we look at the standard linear programming relaxation. To remind you what that was and to remind you what notation I use. So in the fractional knapsack problem, we want to maximize the profits, as usual. We have the capacity, the constraint on the capacity. And the only difference to the binary knapsack problem is that the xi are now basically real valued variables, and they can take values between 0 and 1. So I say for every I, xi can now take any value between 0 and 1. And Eden told us already how to solve that. It's actually a very simple problem. I mean, it's an LP, so it's simple anyway. But you can even solve it without running your favorite LP solver, just by ordering the items according to their density. So let's even assume in the rest of this lecture that without loss of generality, the items are ordered already. And then what you do is you pack the items in this order into the knapsack until the first item doesn't fit anymore completely, and then you take the appropriate fraction of that. Yeah, so we will basically set the first xi to 1. Then you will have usually one fractional xi, which takes a value strictly between 0 and 1, and all the others will be 0. Or to illustrate this in a picture, let me draw a picture which looks almost the same as the pictures I drew last time, but now it has a different meaning. So I will still have the weight on this axis and the profit here. But instead of putting all possible solutions in this picture, I will now really put the items into this picture. So I have n marks in this picture. For each item, I have 1. And yeah, basically, the optimal solution of this fractional knapsack problem has a very nice geometric interpretation. So what you do is essentially you put basically a line here, and then you start rotating in this direction. And in the order in which the items appear, you will put them into the knapsack. Yeah, so you start like this, and then you rotate in this direction, and in this order you put the items in the knapsack. This corresponds to going in the order of the density. And then what's going to happen is that at some point you will have an item that doesn't fit completely anymore, and basically there you stop. Okay? And so the optimal fractional solution contains all these items completely. It doesn't contain any fraction of these items, and it contains this item to a certain fraction. Let me introduce some notation or some terminology. This last position of this ray, where this item is on is usually called the Danzig ray in the literature. Then I will say this item is called the break item. And I will denote it by I star. What else do I need? Well, at some point we will need the slope of this ray, and I will denote that by R. Okay. By the way, so you can compute this solution, of course, in time n log n, since you have to do the sorting first, and then you can do it in linear time. You can also do it in linear time without basically getting rid of sorting first. So that's a nice exercise to think about. But OK, let's not focus on that. Let's see basically how this LP helps us to solve the integral knapsack problem. So let me call in the following X bar the optimal solution to this LP. And let me call by X star the optimal integral solution. Then the idea of this core algorithm, or at this point I should say the hope is that X star and X bar do not differ too much, that they differ only in a few items. And to make this more precise, what we try to achieve is the following. We try to define an area around this Danzig ray, which we call the core. And we would like to argue that if we choose the core in the right way, if we basically make this distance large enough, then the optimal solution X star contains all items above the core. It contains none of the items below the core, and only within the core you have to optimize. And that is the idea of this heuristic. And when I say heuristic, then the only thing that is heuristic is the running time. So it will definitely give you the correct output. OK. So let me again introduce a little bit of notation, not too much. So for an item I will denote by Li the loss of item I, which is simply the distance, the vertical distance of the item to this Danzig ray. So if I look at an item like this, if this is item I, then this would be the loss of item I. Same thing here. So if I look at an item below this ray, then this will be the loss. The loss will always be positive, so it's the absolute value. So formally, I can define that as Pi minus R times Wi. And if I have an arbitrary integral solution X, I will denote by delta of X the set of items in which X differs from the optimal fractional solution. So this will be the set of all items I for which Xi is not equal to Xi bar. And now the first lemma that I'm not going to prove, but the proof is actually quite simple. It's just plugging in the definition, is the following. So for every solution X, for every integral solution, I can exactly tell you what the difference in terms of profit is between the optimal fractional solution and the solution X. And I can do this in terms of these losses. Basically, this difference has two components. The first one is R times W minus the weight of X. And the second component is the sum over all items in which X differs from X bar. And I will sum up the losses of these items. And it's not a very complicated lemma. You can easily prove it by plugging in the definitions. I mean, intuitively, you might think about it as follows. So there are two reasons why the solution X might be worse than the solution X bar. The first reason is it might not use the complete capacity. And this is somehow captured in this term here. So this is basically the unused capacity of solution X. And you multiply it by R. And then solution X can be worse than X bar because it might include some items below the Danzig ray, and it might not include some solutions above the Danzig ray. And the contribution of this is somewhat subsumed in the second term. It's not 100% formal, but that's at least the intuition behind this. OK. And once I have this lemma, I can define the core. I can basically tell you how large I should choose this distance here. So I define gamma as the additive integrality gap. So it's the distance in terms of profit between X bar and X star. And then, I can immediately conclude the following. The set of items in which the optimal integral solution differs from the optimal fractional solution is a subset of the following set. I look at all items whose loss is at most gamma. And I will denote this by C of gamma, actually. Yeah. Why is that the case? Well, it follows easily from this definition and this lemma. Since assume that X star would differ in an item that does not belong to the set. Then, according to this lemma, the difference between X bar and the solution X star would be at least basically the loss of that item. So I can say this is all these terms are non-negative. So basically I can pick an arbitrary I from the set. And I can say this is at least the loss of I, and this is for any I in which they differ. So and if now this solution would differ in an item that has a greater loss than gamma, then I couldn't be optimal, since then my difference would be bigger than this additive integrality gap. So this way, if somebody told me the value of gamma, I could easily reduce my problem. Then I would choose the core in such a way that I only look at items that have a distance of at most gamma from the Danzig ray. And basically, then the only thing I need to do is to solve the remaining instance in the core optimally. Or to make that a little bit more formal, I hope intuitively it's clear what I do, but to write it down, what remains is to solve the following problem. So we have a knapsack problem with hopefully fewer items. So we only look at the items in the core. So basically, we sum over all items in this core. And for those, we have to find the optimal assignment. So I'm looking for the solution that has maximum profit. And now the capacity that is relevant is not the original capacity. I have to take into account that I definitely put into the knapsack all the items above the core. So basically, they are definitely in the knapsack, so I have to subtract their weight from the capacity that I have. So in my notation, I sum over all items I that have a smaller index than I star. By the ordering, these are all the items above the Danzig ray, and I sum over all items whose loss is bigger than gamma, since they are definitely contained in an optimal solution. So I put them definitely into the knapsack, and then what remains is to solve the problem inside the core optimally. And here I assume that these xi are binary. And so the idea is that if this core is small, then only few items remain in the core. So I'm left with an instance that has fewer items, so I can solve that more efficiently. So that's the idea of this core algorithm. Are there any questions up to this point? Well, then I have one. How do I compute the core? I don't know gamma, right? So I have no clue what this additive integrality gap is. I mean, if I could compute that, then probably I could solve the instance optimally anyway, right? So yeah, I don't know how to choose this gamma initially. And if we don't know what gamma looks like, then we just try out different possibilities. So basically, we start out with a small gamma, and then we increase it until we can be sure that it's large enough. And there's an easy way to detect that. And that is subsumed in the so-called expanded core algorithm, or expanding core algorithm. And in pseudocode, this algorithm looks as follows. First step, compute x bar. Second step, set the initial guess for gamma to 0, which usually should be too small. And now we repeat the following. We solve the instance for our current guess of gamma optimally. Or actually, I should put it like that in step 4. We increase gamma by the smallest amount such that the number of items in the core increases. Yeah, or you could also put it slightly different. You start initially with an empty core, and then you increase the distance such that the next item comes into the core. And then, once I've done that, I compute the optimal solution for this core gamma, by which I mean I take all items into the solution that are above the core. I solve the instance of the core optimally. So this is step 5. Yeah, compute optimal solution, optimal integral solution with respect to our current core C of gamma, right? So by which I simply mean we solve this problem. And here's, by the way, the place where we can use what we've seen in the first lecture. Since now you might ask, how do I solve this instance optimally? I use the Nemhauser-Ullmann algorithm. And that is very good for this. First of all, it's quite fast. And second, in the Nemhauser-Ullmann algorithm, you can very easily handle updates in the sense that you get an additional item to your instance. So if you've computed the Pareto curve for your instance and an additional item comes, you just run one more iteration of this algorithm, and you don't need to start from scratch again. That's very convenient for this kind of iterative approach. Yeah, and when do we stop? Let me call this x. Well, we stop until the gap between the optimal fractional solution and x is at most small gamma. And then we return x. And the claim is that x will always be a correct optimal solution to the knapsack problem. And the reason is pretty simple. It's just a very short chain of inequalities. I mean, first of all, if this condition is true, then okay, I have this. And this gap cannot be smaller than the additive integrality gap, right? Since x star is the optimal solution, so this gap cannot be larger than this one. So I have this inequality. And this is my capital gamma. And so I know when I stop, when this condition is met, then the core that we have used has basically size at least capital gamma. And we just argued above that if we choose a core of this size, or an even larger one, of course, then we are optimal. So this way we can really detect that we have found the correct optimal solution. And yeah, this was this heuristic that I wanted to present to you. Let me mention one theorem about it, which is due to René Bayer and Berthold Föcking. They try to explain why this algorithm works so well. And when I say that it works well, then as I mentioned last time, so you can really solve instances with, say, 30 millions of items within a few seconds. So that's pretty fast. And what they proved is they couldn't really do a smooth analysis in the sense that I did it in the last lecture. But what they could do is at least some kind of average case analysis. So they assumed that all the profits and all the weights are chosen uniformly at random between 0 and 1. And the capacity is set to beta of n, where beta is some constant between 0 and 1/2. So these were the kinds of instances they looked at in their analysis. And then they analyzed the expected running time of this expanding core algorithm. And what they proved is that the expected running time is O of n times log n to the power of c for some constant c. And this constant c depends actually on this beta here. So they have, say, an almost linear expected running time. And yeah, this coincides very much with the practical observations you make when you implement this. And the reason, okay, why is this fast? The reason is, of course, that if you choose these instances at random, then usually you don't have too many items in the core. I mean, first of all, this additive integrality gap will be rather small. And then you just have a very small, basically, stripe, and you just need to look at the items in that stripe. And one can prove that with high probability, this number of items is only log squared n. And then basically you can plug in the analysis of the Nebenhauser-Ullmann algorithm, and then you get to this expected running time. But the details of the analysis are pretty sophisticated since you have to cope with all kinds of dependencies. So for example, this Danzig ray is not an arbitrary ray, but it has a small tendency to fall into dense regions where there are multiple, many items. So, and you have to cope with these densities and with these dependencies, which is not too easy. So that's why, yeah, this is maybe not the nicest proof. And it works only in this average case setting so far. So, any questions related to this? That's not the case. Let me come to the more theoretical part of today's lecture. And the question that I would like to ask, as I mentioned before, is which problems get easy when I perturb the inputs and which problems stay hard? And I will formalize this question in a minute. So it's smooth complexity of binary optimization problems. I mean, first of all, to give you an example, we have now seen, okay, the knapsack problem gets easy when you perturb the coefficients in the input. So we have seen this bound of n cubed phi in the last lecture. Now, it's pretty natural to take your favorite NP-hard problem and to ask whether the same is true there. So take, for example, the TSP. So you have a graph, not a metric one, just arbitrary edge weights, and you perturb the edge weights. And question, can we also find an algorithm for the TSP that has expected polynomial running time in terms of the input size and this parameter phi? Or, as I said, pick your favorite problem and ask this question. And now, of course, you could go through all these problems separately, but you don't need to do so since there's actually a very nice characterization. And to give you this characterization, let me first of all tell you which kinds of problems I'm going to study here. So these problems are called linear binary optimization problem. And by that I mean the following. Let me call the problem pi. And an instance of pi should have the following form. It should simply be of the form that you want to minimize or maximize a linear objective function over an arbitrary set of feasible solutions S, where S is an arbitrary subset of 0, 1 to the n. Yeah, so every instance of your problem should have this form, that you can specify a subset of this cube, and you can say, I want to optimize a linear function over the subset. So yeah, if you think about graph problems, I mentioned already in the last lecture that you can usually encode them in such a form. So if you think about the TSP, so you're given a graph, then you introduce one variable for each edge, and you let S be the set of all incidence vectors of tours. Then this corresponds to the TSP. So this way you can capture a lot of different problems. And you can, of course, also capture the knapsack problem by letting S be the set of all 0, 1 vectors that satisfy the capacity constraint. Okay. And I will assume that the coefficients in the objective function are perturbed. So C1 to Cn are phi perturbed. And I will repeat what I mean by that. I mean that we have an adversary, and this adversary can choose basically the set S, and he can choose for each of these numbers a density function. So let me call this Fi, and we do some normalization. We assume that all these coefficients are between -1 and 1. That's is no real restriction. That's just a matter of scaling. And the main restriction here is that this density must not exceed phi. Yeah. And as I mentioned last time, if you don't like to think in densities, then just think about the following setting. The adversary can specify for each number an interval of length 1 over phi, from which it is chosen uniformly at random. This way you clearly see that this phi measures the power of the adversary. So the larger it is, the more precisely he can specify the numbers. Yeah, so that's the model. These are the problems that we study. And the question now is, yeah, which problems pi can be solved in expected polynomial time in terms of the input size and phi? So this should capture, of course, what we did about the knapsack problem. But maybe while I erase the board, you can think why it doesn't capture it quite. So it's not There's one small issue why this doesn't really fit to our analysis of the knapsack problem, but it's not a severe one. So what is the analysis, the difference? Yeah.
Sorry,
Yeah. Yeah. Sure. Yeah.
I'm not sure I completely follow the model. So what is the FI actually affecting? Like in the knapsack, it's affecting the weights, but what is the analog of weights here?
So I mean, it makes sense to have a concrete problem in mind. So let's say we think about the TSP. Then the CIs would simply be the edge weights. So I have a variable for each edge. I let S be the set of all incidence vectors of all tours. And then basically, this vector C contains, for each edge, its weight.
So if, I mean, sorry, so if, I mean, it's not necessary that what you'll get is like forming a metric, right?
No, I'm not saying that, I'm explicitly not speaking about the metric TSP. I'm just, I look at arbitrary TSP. Doesn't have to be metric. You're right, so if you do this perturbation, then most likely you won't get a metric instance, yeah.
So if I pick SAT,
Uh-huh.
3SAT is my
Yeah.
problem, what would the CIs correspond?
Let's see if we can phrase it in that framework. I mean, yeah, you could say these are weights of the clauses, but then you have to be careful what these variables stand for. I mean, I'm not saying that you can basically phrase any problem in this framework. It's, I mean, for sets, yeah, with some tricks you might be able to do that, but I'd rather like to think about graph problems in this context. Okay, any more questions?
So in particular, I mean, that's pretty important difference. Every variable has a weight. And they are not variables with zero weight in the objective function. That's an important difference.
That's an important difference, right. Right, yeah, okay, yeah. You're true, you're right. So in the way I phrased it, you definitely have to have a weight for everything, yeah. Sometimes you can get around that by encoding the set S differently. So basically, that's something, okay. In the context of Pareto-optimal solutions, that works pretty well, but in terms of complexity, probably not. So here you're right. That's one of the weak points of this model, that you cannot deterministically set things to zero. I'm not, so, yeah?
But then you can encode the set S different. You just see in the encoding of the S, you don't allow you take.
I mean, that's true. I mean, what you could do is, let's say you have multiple different solutions that differ only in those coefficients that are set to zero. Then actually you need to consider only one of them. But in terms of complexity, this might make a difference. I mean, in terms of Pareto-optimal solutions, you can really, with these tricks, get around that. But
do you assume that you can decide membership in S?
No, I guess I don't really assume that. I mean, it's no, probably not. But maybe let me phrase one of the theorems. Then it might get clearer. Okay. But maybe any other questions? Well, if not, let me answer my question. Why doesn't our analysis of the knapsack problem doesn't fit entirely into this framework? The reason is, if you think about our analysis, we actually perturb the weights and not the profits of the knapsack problem. Here we perturb the objective function. But that's not really an issue. Actually, our analysis for the knapsack problem would go through in the same way if we had perturbed the profits instead of the weights. That doesn't really make a difference. But OK. So now let's look at these problems. And, well, OK. First question, what's about the TSP? So we can phrase the TSP in this way. Can we solve it in expected time polynomial in the input size and phi? Any guesses? So the answer is we cannot. And there's a more general answer, which is not only valid for the TSP, but in fact, it's valid for every strongly NP-hard problem. So let me remind you what that was. So I say that pi is strongly NP-hard if there exists a polynomial Q such that pi is already hard if I restrict pi to integral instances where every number is bounded by Q. So there's this polynomial Q, and I restrict myself to instances where all these coefficients are integral, and the absolute value is bounded by Q of n, where capital N denotes now the input size of my problem. So for example, the TSP is already NP-hard if you allow only edges with weight 1 or 2. So the TSP is definitely strongly NP-hard in that sense. And now the first thing that I would like to show is that NP-hard problems, strongly NP-hard problems do not get easy if I perturb the coefficients. So maybe one or two more definitions. So I say that a problem has polynomial smooth complexity if I can solve it in expected polynomial time with respect to the input size and this parameter phi. Okay, so in that sense, the knapsack problem has polynomial smooth complexity since I can solve it in time n cubed times phi. So polynomial in the input size and this parameter. And now I can state the theorem that I announced for a while. So the theorem is as follows. If pi is strongly NP-hard, then it does not have polynomial smooth complexity. Sorry?
Can you move the correct form of
should of course say unless, and now it's not unless P equals NP, but unless ZPP equals NP. So ZPP, to remind you, is the set of all problems that you can decide in expected polynomial time. So basically, if you have a problem that belongs to ZPP, this means there is an algorithm, that has, for every input, so in the worst case, it has expected polynomial time, and it always gives you the right output. So this is a slightly weaker statement than saying unless P equals NP. So I'm saying unless every problem in NP can be solved in expected polynomial time. Okay? So, and that is the first part of this characterization. So it's the negative part. So pi is strongly NP hard, so I can't solve it in expected time on these perturbed instances. And let's try to prove that. And actually, I will only prove it for the TSP, but the proof goes through in the same way for any other strongly NP hard problem. Just for the sake of concreteness, think about the TSP. And so what happens in the TSP? I'm given a graph, and I'm given edge weights. And as I said before, I don't care about the metric TSP, but what I care about now is basically this case that proves that it's strongly NP hard. So I care about the 1-2 TSP. So let G be an instance for the TSP with a weight function that maps every edge to either weight 1 or 2. So I know that computing the optimal tour is NP hard in that setting. And now I claim that if I could solve the TSP in expected polynomial time on perturbed instances, then I could also solve it in the worst case. So we do a proof by contradiction. So we assume that it has polynomial smooth complexity. So let A be an algorithm that solves phi perturbed instances in expected time, polynomial in the input size, and phi. And I claim that with the help of this algorithm A, I can optimally solve the given instance of the 1-2 TSP. So what's the trick? What do I have to do? Well, basically, I start with the given instance, and I perturb it. And I perturb it in such a way that I do not change the optimal solution by the perturbation. So the idea, perturb W without changing the optimal solution. And then solve the perturbed instance with A. Okay, so that's the general idea of this. And now let's make that a bit more formal. Let's see how large we have to make the perturbation. So we are given these weights W, and let me first of all define W tilde of E to be W of E divided by 2. This way, I ensure my normalization constraint that every weight is between -1 and 1, without, of course, affecting the optimal solution. I just scale all the weights down so that they are between -1 and 1. And then we choose an interval IE, subset of -1 to 1, with the property that this WE tilde is within this interval. And then, with the additional property that the length of this interval is 1 over phi, where I choose phi to be 4n. Yeah, so I get my worst case instance and I artificially perturb it. And I do this by saying, now choose W prime of E uniformly from this interval IE. And this way, I get an instance of the TSP with perturbed numbers. So I consider now these W prime values. These are perturbed numbers, and so I can use my algorithm A to solve this instance optimally. An expected time polynomial in n, which is the input size, and phi. I set y to 4n, where actually n is now the number of edges, since I have a variable for each edge. So a bit counterintuitive, but in this now n is the number of edges. And so this is polynomial in the input length, since basically the encoding length is at least n, so if I have n edges in the graph. So this way, I have an algorithm that solves an expected polynomial time, this perturbed instance of the TSP. And now the only thing that I need to argue is that the optimal solution I get out of this is also optimal for the original instance I got. And that's fairly easy, because if you look at that, take an arbitrary solution. Then what is the effect of this rounding? So what is the difference between W tilde of x, this way, and W prime of x? Well, I've changed each coefficient by this rounding by at most 1 over phi. I have n coefficients in total, so I've changed the weight of every solution by at most n times phi. So which means, if I plug in the numbers, this is 1/4, right? So if I look at the original instance and the perturbed instance, then I've changed the weight of every solution by at most 1 over 4. And since my original instance is integral, I know that in the original instance, basically, every optimal and every non-optimal solution has a difference of at least 1. So after I do the scaling, the difference is at least 1/2. And since I change every solution by at most 1/4, the optimal solution stays optimal. Since in the worst case, the optimal solution becomes worse by 1/4, the second best solution becomes better by 1/4, but still the optimal solution stays optimal. And this way, this way I get the same optimal solution as before. And I get this solution in expected polynomial time. And that's why, I've now found an NP-hard problem that belongs to ZPP, so ZPP belongs to NP. Okay, is that clear? So I think the main idea is pretty simple. So if the problem is strongly NP-hard, just perturb your instance a little bit without affecting the optimal solution. Then you get an instance that you can solve. assuming that you have expected polynomial complexity. And this way, yeah, you can solve NP-hard problems. So if you don't have questions about this, then what I promised is the characterization. But this is only one direction, right? I said for some problems, you do not get polynomial smooth complexity. But of course, there's a second statement that tells us for which problems we do get polynomial smooth complexity. So somehow our goal is now to make this analysis that we made for the knapsack problem more generic so that it works for a much larger class of problems. Yeah, how can we do that? So I guess I don't need any further definitions. I can immediately give you the theorem. So the theorem is the following. Any linear binary optimization problem that can be solved in the worst case in pseudo-linear time. So what do I mean by pseudo-linear? Well, you might have heard the notion of pseudo-polynomial. Pseudo-polynomial means you have an algorithm whose running time is bounded polynomially in the input size and the largest number that occurs in the input. And when I say pseudo-linear, then I mean that the running time is polynomial in the input size and linear in the largest number that occurs. So if you think again about the knapsack problem, then you know that the knapsack problem can be solved in pseudo-linear time, since these standard dynamic programs that you see in the undergraduate lectures have a running time. I think it's something like n squared times w, where w is the largest weight. So that is something that I would call pseudo-linear. And in fact, this restriction to linear here is not strictly necessary. I could have also written pseudo-polynomial in the usual sense, but then the proof would have been much more complicated. So let's stick to pseudo-linear algorithms. So and I have a problem that I can solve in the worst case in pseudo-linear time. And then the conclusion is, this problem has polynomial smooth complexity. Yeah, so you see if you replace pseudo-linear by pseudo-polynomial, then you almost have your dichotomy. So you have strongly NP-hard problems, which you cannot solve on perturbed instances, and you have problems that can be solved in pseudo-polynomial time, and those can be solved in expected polynomial time on perturbed inputs. Okay, is the statement clear? Okay, then let's try to prove it. Not sure if we managed to do the whole proof today, but let's at least get started and see what the main idea is. So let's say I denote this pseudo polynomial time algorithm as a pseudo. And let's say the running time is O of n to the k for some constant k times c. And first observation is very easy observation. I mean, usually these pseudo polynomial time algorithms solve instances with integral coefficients. Of course, you can do that also with rational coefficients. So if I have an instance where basically each coefficient is a rational number between -1 and 1 and has b bits after the binary point, then I can simply scale all the numbers so that they become integral. And this allows me to also solve rational instances with this algorithm. So a pseudo solves instances in which every coefficient comes from the interval from -1 to 1 and can be specified by b bits after the binary point. In time O of, well, n to the k stays as it is, and now the largest coefficient becomes 2 to the power of b. Since I have 2 bits after the binary point, I scale all the numbers by 2 to the b, so I get an integral instance where the largest coefficient is 2 to the b. Okay? So that's great, but it doesn't help me for our setting. Since in our setting we assumed that we are talking actually about continuous random numbers, so in some sense the encoding length is not even bounded or infinite. You have to think how you encode these numbers, but what you can do is, without affecting the analysis, you could, for example, say I truncate my continuous random variables after a polynomial number of bits. Then every number has a polynomial encoding size, but an encoding size that is still too big to just apply this approach. Okay, so somehow we have to try to get our instances, our instance to an instance that uses only a small number of bits in order to make this algorithm efficient. Yeah, what can you do? So let's say we want to solve such a phi-perturbed instance. So let I be a phi-perturbed instance. So how can I solve I? What would be an approach that uses this pseudo-polynomial time algorithm? So maybe think about how you usually derive a fully polynomial time approximation scheme for the knapsack problem. So you might have seen that in some lecture. So you're given the knapsack problem, you're given some instance, and now what you do is you simply round the profits after a certain number of bits. And basically, if you're given an epsilon, some approximation guarantee that you want to achieve, this determines the number of bits you need. But the number of bits that you need is, let's say the largest number you need in the end is polynomially bounded in the input size and 1 over epsilon. So when you derive this approximation scheme, yeah, you usually do something very simple. You get your instance, you round all the numbers, you solve the rounded instance optimally, and this gives you a good approximation to the original instance. And we will use the same approach here, except that we will argue that rounding preserves the optimal solution. So the simple idea of our algorithm is round all coefficients Ci after a logarithmic number of bits, and and use a pseudo to solve rounded instance optimally. Okay? In the worst case, this gives you an approximation of the optimal solution. And my claim is that on these perturbed instances, it even gives you, with high probability, the optimal solution. Okay, and in order to prove that and to quantify what I mean by that, I have to introduce one notation that we call the winner gap. So what is the winner gap? It's the distance between the best and the second best solution. So I denote it by delta. And delta is so let's say we want to minimize our objective function. So I look at the value of the second best solution minus the value of the best solution. So x star is the optimal solution. So we can write that as we look at all solutions x from our set of feasible solutions. And we take the one with minimum objective function. Okay, so that's the optimal solution to our given instance I. Yeah, just take the solution from S with minimum value C. And the second best solution is x double star. It's almost the same definition, except that we forbid S star, X star. Okay, and this difference is called the winner gap. So how much better is the best solution compared to the second best solution? So in the worst case, it can be 0. I mean, if you have multiple optimal solutions, then this is already 0. And the claim is that on these perturbed inputs, with high probability, this gap has a significant. So it's not 0, and it's not exponentially small. In fact, it's inverse polynomially large. And let me give you the corresponding lemma, which in the literature is often called the isolation lemma. And it says, for every epsilon, the probability that this winner gap is smaller than epsilon is bounded from above by 2n phi epsilon. And let's maybe take a minute to think about that intuitively, what that means. So it means, so plug in, say, for example, epsilon to be, let's write it down explicitly. So the probability that delta is at most, say, 1 over 2n squared times phi is at most 1 over n. So if I view the solutions as follows, I know that every solution has a weight between minus n and n. This is due to our scaling. So all the coefficients are between minus 1 and 1. So all the solutions are between minus n and n. And I want to minimize, so I look for the solution with minimum value on this line. And usually, in most optimization problems, we have an exponential number of solutions. So and each solution has a certain objective value. So each solution corresponds to one dot on this line, which means I have an exponential number of these solutions. So if I look at neighboring solutions, basically the average distance is exponentially small. However, what this tells us is that for some mysterious reasons, the difference between the optimal solution and the second best is quite large. So with probability 1 minus 1 over n, it is inverse polynomially large. So it's much, much larger than the average distance between two solutions. So when I saw that for the first time, I was actually very surprised, So there's really a big gap between the best and the second best solution with high probability. And yeah, this is basically what this idea relies on, because if this gap is big, then basically we can argue that rounding doesn't affect the optimal solution, doesn't change it. Okay, so one thing I should do is now, of course, prove this isolation lemma. Yeah, maybe this is the last thing we do for today, and tomorrow I will tell you how to continue from that point on. So then I claim you have almost seen the proof of this isolation lemma before, namely in my first lecture. There we also analyzed a certain random variable. I guess we called it lambda. But the proof for this isolation lemma is almost the same as we did before. So how does it go? Let me quickly repeat the main steps. So what I will do now is I will define auxiliary random variables, and I will call them delta I. And I will define such a variable or such a random variable for every index I by simply saying, okay, let's say x I equals 0 denotes the optimal solution that for which xi equals 0. So it's the optimal solution among all solutions from S with xi equals 0. And same for xi equals 1. It's the optimal solution for which xi equals 1. And then I will say my auxiliary random variable delta I is defined as the distance between these two solutions. And now there are two claims, the same claims that we had for this other random variable. The first one is that delta coincides with at least one of these delta i's, and we can analyze each of these delta I random variables. So first claim, there exists an I such that delta equals delta I. So why is that? Well, simply pick one index I where the best and the second best solution differ. Then one of them will be this solution, the other will be that solution. So pick any I with x star I not equal to x double star I. So perfect. And the second claim is for every I, we have the probability that delta I is at most epsilon is bounded from above by, I think it should be 2 times n times phi times epsilon. And yeah, also that is pretty much the same as we did before. So it's again this principle of deferred decisions. So I guess I've mentioned that before, but let me repeat it. This is my favorite tool when I analyze random variables. Since I don't know how to handle too much randomness, so usually I just draw almost everything already, and then I wait until only a little randomness is left. And very often this suffices to prove the desired claim. And that is also, so in this case, so fix all the Cj with j does not equal I. then basically I have enough information to determine these two solutions. I mean, I don't know the value of Ci yet, but here the argument is that the solutions that are in this set do not, so they do not contain item I. They are not affected by our choice of Ci. And all solutions in this set contain item I. They are affected by Ci, but I can determine which one has smallest objective value without knowing Ci, since they all depend on Ci. Same argument as last time. So xi0 and xi1 are fixed. And then basically I can write delta I as something like, well, I know that one solution contains Ci, the other does not. So basically I can write it like this, where this kappa is a constant that depends on the choices of the Cj. And then, well, the probability that I care about, that delta I is at most epsilon. This happens only if Ci is close to this constant. Something like this. So I have to be around this constant with a distance of epsilon. So I have an interval of length 2 epsilon. I have a random variable whose density is bounded by phi. So this is bounded from above by 2 times epsilon phi. Now I use the union bounds over all I, and then we have proved the isolation lemma. So here comes the union bound, and then I just have 2n epsilon phi, as we wanted to have. So fairly simple proof, but fairly interesting statement. And now I think I will do the rest tomorrow, but let me say what is missing. So basically, from this lemma, we will easily be able to derive a statement of the following form. If I round all the coefficients after a logarithmic number of bits, then with high probability, the optimal solution is not affected. So I can use my pseudo-polynomial time algorithm to solve this rounded instance, and I will get with high probability the optimal solution. That is the easy part, but that is not quite what we want to have. Because what I promised you is an algorithm that always computes the optimal solution. And this is only an algorithm that has polynomial running time, even in the worst case, but has a certain failure probability. And basically, I want to turn it around. I want to have an algorithm with expected polynomial running time that always gives the optimal solution. And yeah, so in some sense, what we will do is we will do this, and then we try to detect if the solution that we get is really optimal. And if not, we increase the precision and try again. So the interesting part will be how do we detect if the solution is really optimal. But yeah, I will tell you more on that tomorrow.